Okay, so we're going to start off by reviewing the harmonic oscillator. Now, I know that you have done this before, but still we're going to review it. And basically because this is such an important topic. Why do we need it? Well, we're going to use the harmonic oscillator to give a description for free particles, as we have already explained. So now, let me tell you what is the Hamiltonian of the harmonic oscillator. So the Hamiltonian that we're going to study is just given by omega over 2. And then we've got p squared plus q squared. So p is the momentum of our particle. Q is the position of our particle. So we're in a harmonic oscillator potential. And I've got minus 1. Now, why did I subtract 1 here? Well, you might have been used to the situation where your ground state energy was 1/2 h bar omega, okay? That's not what we're going to be doing here. Because I've subtracted the 1, our ground state energy is going to start from 0, okay? So don't worry, there's no physics going on there. I've just decided to subtract things so that we start with a ground state that has an energy of 0 instead of the 0-point energy. So no problem, that's not going to affect anything. Now, I have to tell you, how do you get hold of P and Q? Think in classical mechanics, if you wanted to figure out what was the position of a particle, you'd solve Newton's second law. So that's always the idea in physics. We give some equation that you have to solve to get hold of the quantity of interest. So here too, there would be an equation that you would solve. So it would say the commutator of P and Q is equal to minus I, and I'll put H bar over there, but that's where H bar would go if we were putting the H bars in, but we're not putting the H bars in. So let me remove the H bar. But just to remind you, that's where it would have gone. Now, this is an equation of kinematics. Now, we've spoken a little bit about what kinematics is. So if you were doing classical physics, for example, one of the equations of kinematics would tell you that the velocity is dx dt. It would tell you that the acceleration is dv dt, which is the second derivative of x with respect to t. These equations tell us something about motion and not the specific dynamical situation, the specific force that is acting, okay? So that's kinematics. This is the same for all forces that we study. It's just a statement about motion. In quantum mechanics, the statement of kinematics is precisely this commutator between position and momentum being equal to minus I. That commutator will be the same no matter what force you're studying, what dynamics you're studying. It's the same for all problems that you choose to consider. Okay, good. Next thing I want to say, we are going to have to state what space we work in, okay? So we are going to need to say what space, so what Hilbert space, for example, what's the base of Hilbert space? What space do we work in? And I'm going to write down some equations that might not mean too much to you right now, but later on you'll see that they actually say how big the space is. And we'll see that we use these equations to figure out how big the space is. What these equations tell us, they say, if I have some operator A, and I work out the commutator of the momentum with A, and I get 0, and I work out the commutator of Q with A, and I also get 0, then A must be some multiple of the identity. So this is the identity operator acting on Hilbert space, and lambda is just some real number, okay? So right now, it might not be obvious to you why this is saying how big the space is that we work in, but it will become clear later. So I'll be returning to this particular equation. Good. What do we want to solve? We want to solve the energy eigenproblem associated with this harmonic oscillator Hamiltonian. How are we going to solve this energy eigenvalue problem? Well, we're going to follow Dirac and do it algebraically. So Dirac introduced two operators. So the first operator is Q plus I P, so position plus I momentum, over the square root of 2. Now, remember that Q is a Hermitian operator. It's an observable. All of our observables are Hermitian operators, and P, the momentum, is also a Hermitian operator. So if I work out what is a dagger, well, Q dagger is just Q. The dagger of plus I is minus I, and the dagger of P is just P. And the dagger of square root 2, well, that's just a real number, so it'll just be square root 2. So that's A and A dagger. The kinds of things that we want to do, we want to calculate the commutator of A and A dagger. And in fact, the commutator of A and A dagger is equal to 1. This is an equation that we would like to prove. Now, we're going to be working a lot with commutators. So let's write down a few identities that we will establish for commutators. So here's the first identity. If we've got A plus B, and we want to calculate the commutator with an operator C, well, if we just write out what this is, so by the definition of the commutator, this is A plus B times by C minus C times by A plus B. And then if I multiply these brackets out, I've got AC plus BC minus CA minus CB. The only thing I have to be careful about when I multiply these things out is that I don't change the order of the operators, because these operators do not necessarily commute, so I must respect the order that they are given in. Now, take a look at this term AC minus CA. Well, that I can write as a commutator with A and C. And then the BC minus CB, I can also write as a commutator between B and C. There's another very similar identity, which is that if I took A commutator with B plus C, this is equal to the commutator of A with B plus the commutator of A with C. And you can prove the second identity in exactly the same way that we proved our first identity. And then the last fact that I'd like to tell you about commutators, let's sneak it in over here. This is something that I think you already know. If you don't know, well, just write out the two sides using the definition of the commutator. If we've got a commutator of O1 with O2, this is minus the commutator of O2 with O1. Good. Okay, we will continue in a moment.